What if I told you the secret to making a futuristic quantum computer run, like 50% faster isn't a colder refrigerator,
Right.
or a better microchip,
No.
or even some exotic new topological material?
It sounds completely counterintuitive, right?
Yeah. I mean, what if the key to unlocking the next massive leap in quantum architecture was actually a 100-year-old math equation originally used to study refrigerator magnets?
Yeah, we're just so conditioned to think that the barriers in quantum computing are strictly physical. Like, we assume we just need to build a bigger engine or isolate the qubits better and, brute force our way to utility.
But when you look at the reality of fault-tolerant quantum computing today, the hardware demands are just astronomical.
Oh, absolutely.
You're constantly hitting these resource walls trying to scale up. So today for you, we're going on a deep dive into a really mind-bending shortcut. We're exploring how to drastically cut the operational cost of a quantum computer right now.
And doing it entirely through software architecture.
Exactly.
Right.
Without waiting a decade for the hardware to catch up.
What's fascinating here is how this research proves that algorithmic ingenuity can effectively double the power of the hardware we already possess.
That's wild.
It really is. We're looking at a paper titled Optimal Approximation of Single Qubit Rotations Within a Quantum Circuit. It was published by Gilad Kishoni, Avi Elazari, Ron Cohen, and Lior Gazit, all from Classiq Technologies in Israel.
And honestly, it reads less like a dry computer science paper and more like a brilliant heist.
A heist. I like that.
Yeah, I mean, they basically found a mathematical loophole to cheat the astronomical resource costs of quantum circuit execution. And their lockpick was dusting off the classical 1D Ising model to act as an optimization engine.
It's a remarkable collision of disciplines for sure. But to fully appreciate the heist, we have to look at the vault they're breaking into.
Right. The translation bottleneck.
Exactly. We need to frame the translation problem. Basically why we can't just feed native continuous rotations directly into fault-tolerant quantum hardware.
Okay, since anyone following this space knows we rely on quantum error correction to keep these systems stable, you already know that comes with a strict limitation. The hardware only executes a finite, discrete set of instructions natively. Typically the Clifford plus T gate set.
Right. So if your algorithm calls for an arbitrary, continuous, single qubit rotation, so you need to navigate to a very specific continuous coordinate on the Bloch sphere.
Right. You can't just do it in one fluid motion.
No, you can't. You have to synthesize that rotation by stringing together a sequence of those discrete Clifford and T gates.
And that approximation process is just fundamentally expensive. Let's look at the baseline standard the industry relies on right now, which is diagonal approximation.
Yeah, so with diagonal approximation, you're locking in a target precision, a margin of error we call epsilon.
Okay.
Because you're synthesizing a continuous variable using a discrete gate set, the scaling is logarithmic. Specifically, the sequence costs you a t-count of 3 times the base 2 log of 1 over epsilon.
3 times the log base 2 of 1 over epsilon. That's like the absolute floor, just to synthesize one single rotation along the z-axis.
Right. But a general unitary like an arbitrary movement across the Bloch sphere requires decomposing that movement into Euler angles.
Right, the XEX sequence.
Exactly. You generally need an x rotation followed by a z rotation followed by another x rotation.
Which means we multiply that baseline cost by 3. So you're suddenly looking at a total t-count of 9 times the log base 2 of 1 over epsilon.
Precisely. The cost just balloons instantly.
Okay, let's unpack this for a second. It's like having to translate a really beautiful, nuanced Shakespearean monologue into a language that only has a 100-word vocabulary.
That's a great way to put it.
You're going to need paragraphs of clunky text to convey what could have been said in a single precise sentence.
Right.
And the clunky text here is the long sequence of t-gates.
Oh.
But, and I have to push back on the premise of the paper itself here for a second.
Go for it.
Why the hyperfixation on the t-gate metric? Like, they isolate it completely in their optimization Hamiltonian.
Right.
Why not minimize overall circuit depth or total gate count across all the Clifford operations?
Well, because the fault-tolerant overhead for T-gates absolutely dwarfs everything else.
Wait, really? Everything else?
Oh, yeah. If you look at surface code architectures or magic state distillation protocols, Clifford operations like CNOTs or polygates, they're relatively cheap. They can be implemented transversely.
Oh, okay.
T-gates cannot. Executing a single T-gate requires generating, purifying, and injecting a magic state. And that consumes just an enormous amount of physical qubits and cycle time. They are the undeniable bottleneck.
Wow. Okay. So if T-gates are the inescapable bottleneck and diagonal approximation locks us into that rigid 9 times log cost, we literally can't build our way out of this with hardware anytime soon.
Yes, exactly.
We need a fundamental mathematical loophole.
Which brings us directly to the paper's proposed cheat code, magnitude approximation, or MA.
The 3x discount.
That's the one. Magnitude approximation fundamentally alters the constraints of the synthesis problem. Instead of rigidly fixing all the parameters of the unitary, MA relaxes the approximation.
It allows the global phase and certain orthogonal rotations to just float, right?
Exactly. By loosening those parameters, you can synthesize the target rotation with the T count of just 1 times the log base 2 of 1 over epsilon.
Dropping the multiplier from 3 down to 1. That is an instant 66% reduction in T-gate cost for that specific rotation.
Yep.
But obviously in quantum mechanics, there are no free lunches.
Huh.
What exactly happens to those floating parameters? Like, where does the mathematical slop go?
Yeah, well, that massive discount leaves behind residual errors. Specifically, it leaves arbitrary rotations parameterized as angles alpha and beta around the orthogonal axis, and these just sit right before and right after the gate you just synthesized.
It's like a chef chopping vegetables at triple speed, but just throwing the scraps all over the counter.
Exactly.
I mean, chopping faster only saves you time if you can effortlessly sweep that mess onto the next chef's cutting board. Someone who is already going to make a mess and can deal with it.
Right.
Because if you have to stop and synthesize additional T-gate sequences to clean up those alpha and beta residuals yourself, you've completely negated the 3x discount.
That is exactly the dynamic. To make magnitude approximation viable, you have to absorb those arbitrary residual errors into neighboring gates in the circuit.
You don't execute them, you merge them.
Precisely. And this relies entirely on commutation relations.
Because in the actual topology of the circuit, you don't just have single qubit rotations sitting in a vacuum, you have entangling gates.
Primarily CNOTs, yeah, connecting the qubits.
Right. And the mathematical beauty here is that these residual rotations can basically propagate through the circuit structure.
Exactly. An RZ gate rotation around the z-axis commutes with the control qubit of a CNOT gate. Similarly, an RX gate commutes with the target qubit of a CNOT.
So they just slide right past the entangling operations without altering the underlying logic of the circuit at all.
Yeah. They hop over the CNOTs until they bump into an adjacent single qubit rotation that is operating on the exact same axis.
Oh, wow.
And once they meet, 2 adjacent rotations on the same axis can mathematically be merged into one single rotation.
So the residual mess is just absorbed without adding a single new T-gate to the total cost.
Exactly.
Wait, okay. If magnitude approximation gives us a 3x discount, and we can just use commutation to sweep the residuals into other gates, why not just be messy everywhere?
Oh, I see where you're going.
Yeah, why not aggressively apply MA to every single rotation in the entire circuit? Take the discount on everything.
Well, think about your kitchen analogy. If every single chef is sweeping their scraps onto the next counter, the dirt cascades. If you apply MA everywhere, you generate an absolute avalanche of alpha and beta residuals. Eventually, they hit boundaries where they cannot commute.
Right, or they bump into other residuals rather than clean targets.
Exactly. You run out of sponges to absorb the mess. You end up with orphaned residuals that you are forced to synthesize independently.
Which massively spikes your T-gate cost.
It actually makes the circuit far worse than if you just used the baseline diagonal approximation.
Wow. Okay, so it's a strategic balancing act. You have to look at the entire circuit holistically and decide, okay, I'll use the messy, cheap MA right here, but I will deliberately use the clean, expensive diagonal approximation right next to it, specifically so it acts as a sponge.
Yes, exactly. For every single rotation segment in the circuit, you have to make a binary choice, MA or diagonal.
And you can't make that decision locally.
No, you can't, because if you choose MA on qubit 1, its residual might hop over a CNOT to qubit 2.
Which changes the optimal choice for the adjacent segment on qubit 2.
Right, which might then propagate an error down to qubit 4.
So the dependencies map out across the whole algorithm.
Exactly. It requires a global optimization. You have to delegate the approximation types across the entire circuit simultaneously.
And that is a terrifying combinatorial nightmare.
Oh, it really is.
For a circuit with n rotation segments, you're looking at 2 to the power of n possible configurations. If you have a circuit with just a few hundred segments, which is tiny by fault-tolerant standards, the number of possible configurations vastly exceeds the number of atoms in the observable universe.
Yeah, you can't guess and check.
You certainly can't brute force it.
No. Brute forcing a global minimum on a 2 to the n search space is a classic computationally intractable problem. And this is the masterstroke of the Classiq team's paper.
Yes.
To navigate this impossible quantum software problem, they mapped it to a foundational classical physics model from the 1920s.
Okay, here's where it gets really interesting. They realize this entire balancing act maps perfectly to the 1D Ising model.
Specifically, the 1D Ising model with a spatially varying field.
Right.
Historically, the Ising model was formulated to understand ferromagnetism, like how atomic magnetic spins align themselves in a material to reach a state of minimum thermodynamic energy.
I love this framing so much. It's like mapping city gridlock onto a Sudoku puzzle. Let's walk through how they actually built this bridge, because mapping a quantum compiler problem to physical magnetism is just wild.
It is. So first, they parse the quantum circuit into discrete segments. A segment is defined as the rotation situated between two consecutive CNOT gates on a specific target qubit.
Okay.
They pre-process these segments into a canonical form, just ensuring each one has a minimal standard set of rotations. Then they assign a binary variable to each segment, a spin, denoted as sigma I.
And since it's a spin, it can only be +1 or -1.
Exactly. A spin of +1 represents the decision to apply magnitude approximation to that segment. A spin of -1 means applying the diagonal approximation.
So it's like a row of interlocking puzzle pieces where each piece can either be flipped face up or face down.
I like that.
You want as many pieces face up the MA choices as possible because they give you points, or in our case, save you T-gates. But if a face-up piece is placed next to a face-down piece, their edges clash, and you get penalized. The Ising model naturally calculates the absolute best configuration to maximize the points while minimizing the clashes.
That's a highly accurate way to visualize it. To formalize that mathematically, they constructed a Hamiltonian.
Okay.
In physics, a Hamiltonian describes the total energy of the system, and physical systems naturally seek their lowest energy state. In this paper, lowest energy is perfectly synonymous with lowest total T-gate count.
And their Hamiltonian has two highly specific components governing those spins, right?
Right. The first is the local field, denoted as HI. This represents the intrinsic isolated benefit of assigning spin +1 or MA to that specific segment. It's calculated based on Ri, which is the number of single qubit rotations physically confined within that segment.
Oh, I see. So a strong HI local field is the math essentially yelling, hey, there are a lot of rotations trapped here. The 3x discount is going to save us a ton of gates.
Exactly. It pulls the spin toward +1. But then you have the second component, the interaction term, denoted as J. This represents the coupling between adjacent segments I and I+1.
Right. This is the clash of the puzzle pieces. This is where the model accounts for the residual mess.
Precisely. If segment I is set to MA, it generates a residual error that commutes across the boundary into segment I+1. If segment I+1 is set to diagonal, it can absorb that error.
The sponge.
Exactly. But if they're both set to MA, or if their spins are misaligned relative to the commutation rules, you have a mismatch.
And mathematically, why does that mismatch represent a penalty?
Because an unresolved mismatch means that residual error is orphaned. You now have an arbitrary alpha or beta rotation floating in the circuit that cannot be merged.
Oh, right.
You're forced to synthesize it natively using a fresh sequence of T-gates. That directly increases your T-gate cost, which the Hamiltonian registers as a spike in the total system energy.
Makes total sense.
Yeah, and the J term accurately quantifies that penalty based on the number of rotations that actually cross the boundary between those two segments.
It is stunningly elegant. I mean, they took a seemingly impossible 2 to the n exponential mountain and flattened it into a one-dimensional chain of magnets, constantly negotiating with their immediate neighbors to find the most comfortable, lowest energy alignment.
It's a perfect mapping, but identifying the mapping is only half the battle. You still have to solve the Hamiltonian to extract the optimal configuration of MA versus diagonal segments.
Right, but wait. Because they proved it maps to a strictly 1D chain with nearest neighbor interactions, they don't have to check every combination at once, do they?
Right.
They can utilize the Markov property. You only ever need to know the state of the puzzle piece immediately to your left to decide the optimal state for the piece you are holding.
You've just hit on the core of why this works. Because of that Markov property, they don't face an exponential search. They can employ dynamic programming to solve the entire system in linear time.
Or O of n complexity.
Exactly. As the depth of the quantum circuit grows, the time it takes to optimize it scales in a straight line, not an explosive curve.
That's huge.
It is. The algorithm basically executes a Viterbi-like decoding process. It sweeps through the segments from left to right in a single forward pass.
Okay.
And for every segment I, it calculates two cumulative energy paths. E plus I, which is the absolute minimum energy required to reach this segment if you force it to be MA, and E minus I, the minimum energy if you force it to be diagonal.
Right. And as it computes E plus and E minus for, say, segment 3, it's looking back at the values from segment 2, applying the intrinsic HI savings, and then adding or subtracting the J interaction penalty depending on whether the spins align or clash.
Right, and critically, at each step, it drops the suboptimal path. It only stores a pointer mapping back to the state of the previous segment that yielded that minimum energy.
Oh, so it just sweeps all the way to the final segment of the circuit, looks at the final E plus and E minus, and just picks the smaller number.
Yeah.
And that number is the guaranteed absolute global minimum T-gate cost for the entire algorithm.
And then comes the backtracking phase. Once it identifies that global minimum at the end, it just follows those stored pointers backward through the chain, reading out the definitive optimal sequence of MA and diagonal assignments.
That is just brilliant.
Linear time, exact global optimization, no heuristic guesswork.
That is software engineering at its absolute finest. But, math in a vacuum is one thing. The paper actually put this through its paces, right?
So they did.
They benchmarked the algorithm against standard synthesis protocols, and the real-world payoff is what really makes this a game changer.
The data is definitive. They started by testing it on purely random quantum circuits, dense, unstructured algorithms that act as a brutal stress test for compiler routing and optimization.
Right, the worst-case scenario.
Exactly. Even on that chaotic topology, the global Ising optimization achieved an average 26% reduction in total T-gate count compared to the baseline.
A quarter of the resource overhead just evaporated on worst-case random circuits. But where my jaw actually dropped was when they applied it to structured, real-world molecular simulation circuits generated by the Classiq platform. These are the actual algorithms quantum chemists are trying to run today.
Right. The topology of highly structured algorithms naturally creates more opportunities for those residuals to commute and absorb, and the results absolutely reflect that.
So what were the numbers?
Well, for a basic molecular simulation like hydrogen-2, the T count dropped by 13%. For an H2O water molecule simulation, the T-gate cost dropped from over 11,000 down to roughly 8,100.
A 29% reduction.
Exactly.
Yeah.
And then there is the UCCSD circuit.
Oh, man. For anyone unfamiliar, unitary coupled cluster is this massive, incredibly deep ansatz used in variational quantum eigensolvers for complex quantum chemistry.
Right.
It is the poster child for algorithms that basically break near-term hardware because the gate depth is just so punishing.
Yes, it is. The baseline T count for their UCCSD benchmark was 28,493.
And the dynamic programming algorithm slashed that down to 11,883.
An unbelievable 58% reduction.
58%.
It strips out over 16,000 T-gates without losing an ounce of target algorithmic fidelity.
So what does this all mean for you? If you're listening to this deep dive right now as a researcher, maybe an enterprise architect, or an investor tracking the quantum timeline, why should a 58% reduction in a UCCSD circuit make you stop what you're doing?
Well, if we connect this to the bigger picture, a 58% reduction effectively cuts your required hardware resources in half.
Wow.
In the current era of quantum computing, we are fighting for the survival of every single coherent qubit. The bottleneck for discovering new life-saving drugs or designing ultra-efficient battery materials isn't the theory.
No, the theory is there.
Right, it's that the quantum hardware required to run the simulations just doesn't exist yet.
But if you can achieve the exact same algorithmic precision, using half the magic states, half the routing overhead, and half the coherence time, you don't need the hardware of 2035 to run these algorithms.
Exactly. You can run them on the hardware of 2030. You're essentially doubling the computational density of the machines we are building today.
The timeline to quantum utility literally just shifted. And the catalyst wasn't a breakthrough in cryogenics or materials science. The software just leaped ahead by standing on the shoulders of classical physics.
You really did.
So to wrap up this incredible journey we've been on, fault-tolerant quantum computing is shackled by the massive cost of T-gates required to translate continuous rotations.
Right.
The standard diagonal approximation is safe, but scaling it is prohibitively expensive. Magnitude approximation offers a massive 66% discount per rotation, but it litters the circuit with residual errors that will cascade and break your algorithm if left unchecked.
And by mapping that exponential balancing act onto the classical 1D Ising model, the researchers at Classiq successfully deployed a linear time dynamic programming algorithm to globally orchestrate those residuals.
Perfectly absorbing the mess.
Exactly, and literally halving the cost of enterprise-scale quantum simulations.
It's the ultimate heist pulled off in O of N time.
The elegance of mapping the bleeding edge of quantum computing onto a model originally designed a century ago to explain how iron becomes magnetic is just profound.
It really is.
It proves that innovation isn't always about inventing new math. Often it's about finding the right translation. And this raises an important question for you to explore on your own.
I'd love to hear it.
As the architecture of quantum computers becomes increasingly complex, what other ancient, deeply understood classical phenomena in physics or nature might secretly hold the blueprints for navigating the quantum bottlenecks of tomorrow?
That is absolutely something to mull over. The universe clearly likes to reuse its best tricks. Thank you for joining us on this custom-tailored deep dive, and remember to stay endlessly curious.